A normal distribution has this nice curve that we call a bell-shaped curve. And it's when we have continuous data around a central point, so right in the middle, that's your mean. And there's two parameters that describe your normal distribution. They're your mean and your variance. How your variance shows up is that almost all the data is 3 standard deviations above or below the mean. And when something has a normal distribution, we're going to learn that with just those two numbers, you know a ton of information about it. You can describe the group of people or whatever the data is you've collected really, really well, just with knowing the mean and the standard deviation. In fact, this is the first important bit of data. Okay? Just like our histogram that we drew on our calculator here, each of those bars represented a probability. Right? So this probability here is getting 5. You've got a 24% chance. If you flipped a coin 10 times and got 6 heads, the chances of that are 20%. It should make sense, the symmetry, that getting 6 heads would be the same as getting 4 heads, because when you get 4 heads, you get 6 tails. And it shouldn't matter. You shouldn't be like more likely to get 6 tails than get 6 heads. So we have symmetry here. And as you get further away from the mean, right, the mean of this data would be 5. That would be our expected value. As you get further away, the probabilities decrease.
So this one, like on the histogram here,
Yeah.
This is for discrete data. So
This is for discrete data.
So it still has the same shape, but for continuous data, it would be more.
Continuous data is a perfect curve.
So like the stuff that we've done so far is for discrete.
The stuff we've done so far is discrete. We're going to find out that for certain discrete data, at a certain point, you can use the normal curve as an estimation that's really accurate. Because if I did this for 100 trials, right, what's going to happen to all of my little bars? They're going to appear to be smaller because I've spread it out over 100. And it's going to get closer to the curve. And if I did 1,000, it would be really close to the curve. Sort of. Seems sort of like calculus and integration that we're getting towards. Same similar idea. Okay? And so when you have a normal distribution, your mean is in the middle, and you can say that one standard deviation above the mean, there's going to be 34.1% between that mean value and one standard deviation. Exactly 34.1%. And then, as you go further out, between one standard deviation and 2 standard deviations, it's exactly 13.6. Well, not exactly. If you actually go, the decimals keep going. But it's similar to that. The idea that the whole area under that curve is 1 is kind of like your probability distributions. Right? Your probability distributions, if you added them all up, they add up to 1. So that histogram added all up to 1. Now the curve is smooth. It also still adds up to 1. And just like the histogram, that bar represented the percentage. If we think of the area, right? If I think of, let's go back to the middle one because it's the biggest. It looks like you're on the podium. What is the length and width of that rectangle? Well, I should say the base is 1. The height is 0.246. Can you see that the area of that rectangle is equal to 0.246. Okay? And if we added up all the areas of the rectangle, that would be exactly the same as all of the probabilities, and it would add up to 1. That's connected to our normal curve, because all of this area underneath, we imagine a bunch of tiny rectangles, well, they would add up to 1, because that would be 100%. Okay, so the area under the curve represents the probability. Now, it's often that they have this rule called the 68, 95, 99.7 rule. Okay, it is probably the most descriptive rule ever, because if you know the name of the rule, you know what it means. The 68 means that if you are between one standard deviation above and below, that area is approximately 68. You can see from there it's 68.2, but they called it the 68 because 68 is close enough. Okay? If you add up all the numbers, 13.6, 34, 34, and 13.6, if you add up all of those numbers, that's really close to 95. So you know that 95% of your data lies within 2 standard deviations of the mean. And finally, 99.7, which is really, really close to 100%, as soon as you go 3 standard deviations above and below, you have almost everybody. So for our experiment, right, we flipped a coin 10 times. The mean is 5. That part is easy. How would we calculate the standard deviation of our experiment where you flip a coin 10 times? Do you remember the formula for finding the standard deviation of a binomial distribution? Square root, number of trials, times probability of success, times probability of failure. 1.58. If you add 1.58 3 times, that's 4.5. Okay? If you subtract it 3 times, that's 0.5. When flipping a coin 10 times, does it make sense that 99.7% of the time you're going to get somewhere between 0.5 and 9.5 heads? Okay? It's very rare to get no heads or to get all heads. So that would be outside of 3 standard deviations. Okay? If I go 1.58 up from 5, that's at 6.5, down 3.5, approximately 68% of the time, you should get between 4.5 and 6.5 heads. Okay, that doesn't really, since it's not continuous, those numbers don't make sense. But it gives you an idea of where things are. If we did more trials, if you did 100 trials, at 100 trials, your standard deviation is 5. This number makes more sense. And if we use this number, your mean is still going to be 50 at 100 trials. Does that make sense? 68% of all the data will be between 45 and 55 heads. Okay? Between 40 and 60, 95% of the time, you're going to do this. It's really rare to get more than 60 or less than 40. And from 35 to 65, that's going to happen almost 100% of the time, 99.7% of the time. So again, if you're a bet, no, I won't go there. But now you can leave something up to chance, and you know what the probabilities are of that happening. Ooh. So that was our 68, 95, 99.7 rule. we have a standard normal distribution and a normal distribution. What the standard normal distribution does is it says, let's just change our mean to 0 and count standard deviations as 1. And then that would make a standard normal distribution. And then there's a nice fancy Greek letter. Anybody know their Greek letters really well? No. I think that's phi. Phi, phi, pho, or phummy, I'm not sure. Okay. If you have a standard normal distribution, like this, you can find what we describe the scores along there, we describe them as z-scores. And a z-score is just how many standard deviations you are above the mean or below the mean. Ooh, we should challenge the other class. Challenge them to a test. See who, go home, start practicing guessing stuff and get really good at, can you get better at guessing by guessing more often? Is it something that with practice you get better at? Like, yes and no? You think it's like 5, 3. Okay, I got to keep practicing. 4, 3. I need more. 7. Oh, that's a bad guess. Okay. Right? Perhaps you could get better by realizing you should never guess 7 when rolling a die. So maybe there are some aspects of guessing that you could get better at, but I don't think any amount of practice will get you that much better at guessing. Okay? But we could have a guessing competition. Okay? And we could find out who is the best guesser of all of us. Okay? Maybe I'll set that up. I'll talk to Mr. LaFrance, and we could have a guessing competition. Guess on 50 things. Okay. Here's a formula you do not need to know. Is it in your book? I don't think we even include it in your book. Here's the function that takes the mean, the standard deviation, and any score into consideration. And calculates that curve. So if you wanted to graph, if we go back, if you wanted to graph that curve, you would have to type this into your calculator. Of course, in this case, the mean was 0. The standard deviation is 1. So you'd plug in all of the values. And it's got a nice formula. Hey, it's got e and pi in it. Okay? So much fun. So if you ever wanted to graph it, you could. You'd have to type that into your graphing calculator, into the equation. The mean, the median, and the mode are all the same. And everything is symmetrical. Okay. So there's a blank page to make you happy. And right here, we're going to get introduced to another thing on our calculator, Normalcdf. And we're going to use Normalcdf because you're cumulative, you're adding up the area from one lower score to one higher score, given a mean and a standard deviation. Okay? If you don't put in the mean and standard deviation, it's going to just assume it's standard normal. So let's find that on our calculator and see what we have. Second distribution. Normalcdf is easier to find. It's number 2. The lower bound. I'm going to put 3. Upper bound, 5. My mean, I'm going to do that coin flip one that we did 100 times. No, if we did it 100 times, we're not going to figure out between 3 and 5. Let's figure out the chances between 45 and 55. Okay, yeah, I'll do that. What was our mean when you flip it 100 times? 50. Do you remember what we calculated our standard deviation to be? 5. So if we paste it, it tells us 68.26. Does that make sense based on our 68, 95, 99.7 rule? Yes. That if you flip a coin 100 times, your chances of getting between 45 and 55 heads would be 68%. Now the normal CDF, and I'm going to go back to it again, what's nice about it is that one we could have estimated. Right? But if you wanted to say between 49 and 51, that one we can't estimate. What do you think the chances are of getting either 49, 50, or 51 heads if you flip it 3 times? And of course, we're using the normal distribution. This would just be an estimate. 16% chance. It's kind of interesting, right? Could you convince someone that it would be less? Probably. Like, well, there's all these possibilities. There's from 0 to 100. There's 101 possibilities. And we're only looking at 3 of them. Shouldn't the probability be less? No. So we can figure out any values within here. And the normal CDF puts that in. And it calculates the area under the curve between those 2 values. A lot of human data follows a normal distribution. So you guys are almost 18, some of you 18 already? No, not till next. I have to wait a little bit, right? Okay. Humans are normally distributed. That's why when you see someone who's 7'8", you go, whoa, that's really rare. Because that falls out of the normal distribution, either really, really tall or really, really small. Okay? Chest measurements of 18-year-old males have an average of 95 centimeters and a standard deviation of 8 centimeters. If the data has a normal distribution, what is the probability that an 18-year-old male has a chest size between 87 and 103? So we can draw out our normal distribution. And it's quite handy to draw this out every single time. Draw the bell curve, put your mean in the middle, take your standard deviation, which is 8, add 8 3 times, so I have 103, 111, 119. Subtract 8 3 times, 87, 79, 71. I then like to shade what you're trying to find. We're trying to find the probability between 87 and 103. That's the area we're trying to find. Could you estimate this without a calculator? What percentage should be between 87 and 103? 68. We go to our calculator, do normal CDF, round it to 3 sig figs, remember the approximation sign. We get 68.3. Yes. Okay. And same thing, we can find what is the probability that an 18-year-old male has a chest size less than 87. And so this one introduces you to this notation. Okay? -1 E99 is scientific notation for -1 times 10 to the 99. which is a huge, huge negative number. The number that I entered in red, you do have some options here. For example, in this case, retype this in and put 0 instead of that. Okay? We are trying to think theoretically and realistically. If a male had a chest size of 0, he'd be really, really scared. Well, he wouldn't exist. Okay? But going to negative 10 million also is like overkill. Put in 0 there. So let's go to Normalcdf. Oh, is mine working yet? Okay, mine's working again. Good. So second distributions, Normalcdf. Plug in 0, an upper of 87, mean 95, standard deviation 8, 15.9, same number. Where is 99.7% of our data? Plus or minus 3 standard deviations. So even at 71, our answer would be very similar. But at 71, our percentage might be off a little bit. But if you went another, let's just try, and go back to my calculator. I'm going to change my lower one to 50. Instead of 0. And check how the number changes. At what decimal place does it change? Right, all the numbers are the same until like the second last digit, 9 instead of 0. So to 3 sig figs, 50 would be enough. Okay? To 3 sig figs, if you want to find something less than something, the minimum you would have to set as your lower is probably 5 standard deviations below. So if I went, 5 times 8 is 40. If I went down to 55, I'd probably be more than likely fine. The negative 1 e to the 99 is an overkill, but it works. It for sure will give you the exact answer all the way. Same thing if you have something that says greater than, right, greater than 87. You can use this idea, since we know that there's 16% less, there's going to be 84% above. 84.1 to 3 sig figs. We could also get the greater than with our Normalcdf. Now the lower value would be 87. The upper value could go 1 e to the 99, 95, and 8. Push enter, and you will get the 84.1% as well. So again, a lot of stuff that we use our calculator for. The weights of chocolate bars produced by a machine are normally distributed with a mean of 232 grams. That is a big chocolate bar. How big of a chocolate bar is that? Like I think the Lindt chocolate bars that are this size are 100 grams. It's just like, whoa. That's nice. And a standard deviation of 3.6 grams. So companies that produce products that put the weight on them, like when you buy a bag of chips, what's the weight of a bag of chips usually? Do you know these things? Do you ever look at the weights? Do you ever pick your chocolate bar, the one that's heaviest, if you're really hungry? Yes? What chocolate bars are heavier?
I do that. Mostly on low hungry.
There you go. You get more weight. You're like, I'm hungry. Chocolate bar costs the same. That's going to fill me up more. Yes. I do that too, especially if you have like 2 chocolate bars that are like so similar. Like what are chocolate bars that are almost identical? Mirage and Aero, are those like Snickers and Mars? They're kind of similar. So then you can look at the weight. Oh, this one I'm getting a little bit more for my money. Okay. Find the proportion of bars that can be expected to weigh less than 233.91 grams. Just a random decimal number there. So we can draw our normal distribution. This time, right, 232 is our mean. I added 3.6, added 3.6 again, added 3.6 again. 233.91 is somewhere in between 0 and 1 standard deviation above. Looking at that, and you had to estimate the area or estimate the probability, can you see that an estimation of above 50% is good? It has to be more than 50% because it's more than half. There's the picture on your calculator. If you went normal CDF from -1, e to the 99, up to 233.91 with a mean of 232 and a standard deviation of 3.6, you get 0.702. So try typing that into your calculator to see if you get the same value. In a normal distribution, the weights of babies born at a certain hospital average 3.6 kilograms, with a standard deviation of 0.4. So now we can take something like this, they have the data for it, and you could say, what are the chances of having a baby more than 4 kilograms? What percentage of babies happen that night that weigh more than 4 kilograms? Again, start by drawing your normal distribution. Quickly sketch it. Draw 3 standard deviations above, 3 standard deviations below. And before we calculate this, I want you to use the 68, 95, 99.7 rule and get an estimate for that area. I'm going to actually calculate in my calculator to get all the decimal places. Oh, I think it's going to be identical to that one. Is it? Yeah? Okay, I'm going to store that as x. What happens in these questions is sometimes you're going to get binomial distribution and normal distribution combined. So part A of the question is like this. It says, this is at a hospital, this is the mean, this is the standard deviation. What are the chances that you get a baby that weighs more than 4 kilograms? 16% chance. Okay? Part B says, on a really busy night, 20 babies were born at the hospital. Okay? That night, 5 babies were over 4 kilograms. What are the chances of that? That's part B to this question. One night, 20 babies are born. 5 are more than 4 kilograms. 4 kilograms or more. What are the chances of that? And then it becomes a binomial distribution question. Because you know how many trials there were? 20. You know the probability of success because you calculated in part A. There's a 16% chance of getting. What are the chances of getting 5 successes? So we can go to our calculator. Find out exactly 5 babies. Whoa, that's not the one I wanted. Yeah, it's the fish distribution. I did it again. What is happening? Binomial is this one. I'm on that one, right? I was on that one the last 3 times. Oh. Oh yeah, here we go. Try it one more time. Not the first time, and then I didn't exit out of there. Let's try this. Perfect. 20 trials, 20 babies. Probability of success. I wonder if I put x in here if it remembers the value of x. We're going to try it because I stored it as the value of x. And we want to find exactly 5 babies. There's an 11.6% chance of that. I'm going to just see if that is roughly the same if I actually type in 0.159. Should be relatively similar because I've rounded now. Yes, so that storing as x worked. Okay? But can we go from a normal distribution question to a binomial question mid-question? It's going to happen. You're going to mix things up like that. And then part C would probably have logarithms. Anyways.